Good afternoon, and I welcome you all to this lecture session of the course Laws of Thermodynamics. Now, last class we discussed the Carnot's, we were discussing the Carnot's theorem or Carnot's principle, and we arrived at that conclusion by a logical deduction or proof that a reversible engine, efficiency of a reversible engine is higher than that of an irreversible engine operating between the same source and sink. Now, the second part of this statement is that efficiency of all reversible engine operating between same source and sink is the same. How we take two, how do you prove that? We take two, it is very simple. The way we prove the first one, it will automatically follow. That means if there is two reversible engines, R1 and R2, both are reversible in this case. Earlier, one reversible, another irreversible. Let Q1 R1 is the heat taken by the reversible engine 1 and Q1 R2 is the reversible engine 2. And these are the heat rejected by the reversible engine 1, reversible engine 2. Accordingly, this is the work developed by the reversible engine 1, this is the work developed by the reversible engine 2. Okay. Now, let us consider the way we did earlier, that eta R1 is less than eta R2. Eta R1 is less, the way we consider, this is reversible, this was irreversible. Then by definition of efficiency, and you at the same time consider that Q1 R1 is similar way, that means the heat taken by two reversible engine is the same, but their rejection is different. Accordingly, the work done is different because we don't accept first that their efficiencies are same. First we assume that eta R1 is less than eta 2. Then if we make these two operate as a heat pump, reversible heat pump or refrigerator, then all these quantities will be same in the opposite direction and it will demand and work WR1 from the surrounding. And if this is so, WR1 is less, that means the earlier proof eta WR1 is less than WR2. So therefore, a part of WR2 will be taken by WR1 and we get a net work output of WR2 minus WR1. Clear? Because last proof, if you recall the last proof, then you will see that WR2 is greater than WR1. So we take this and we get a net work. That means by reverse this, we can prove that eta R1 cannot be less than eta R2, because in that case it will violate the Kelvin-Planck statement. We connect this and we prove that. Now, the difference is that this is again a reversible engine. Now, if we reverse this, now eta R1 cannot be greater than cannot be less than eta R2. Let us consider eta R2 is less than eta R1. This is less than this. Then what happened? What we do? We just reverse it. This is a reversible heat engine and all these quantities will prevail by the same amount, but in the opposite direction. It will take Q2 R2 from here, it will give Q1 R2 here and it will take WR2 there. So if eta R2 is less than eta R1, then WR2 in this case is less than WR1 and we can connect this, and in that case we get an network WR1 minus WR2, and if we connect these two, that means it violates the Kelvin-Planck statement. That means in this case what we can do, we can reverse this engine if we consider efficiency of this is less than this, and we prove that the way I proved earlier, that efficiency of this engine cannot be less than this, otherwise it will violate the Kelvin-Planck statement by linking these two, because this heat added is same. But if we consider eta R2 is less than eta R1, then we reverse this, and here we have that opportunity or that advantage that since it is a reversible heat engine, so if you reverse this quantity will be same and in the opposite direction. Since in this case WR2 is less than WR1, we will take WR1 a part of this and WR1 minus WR2 is the net work output and we will connect this. So this way it will violate Kelvin-Planck statement. So therefore, eta R2 cannot be equal to eta R1. So eta R1 cannot be less than eta R2, eta R2 cannot be less than, sorry, not equal to, cannot be less than eta R1. So only opportunity, only solution is that eta R1. That means this can be proved that for any reversible engine operating between the same source temperature and sink temperature. That means same heat reservoirs operating between the same two heat reservoirs, efficiency is same. And now you can have a question, sir, what are the difference between the reversible engines? Yes, the reversible engines, two reversible engines may differ by the construction of their material of construction, by their design. The processes may be different. Reversible process may not be that. The reversible process, there may be constant pressure reversible process, constant volume reversible process, isothermal reversible process. So the processes, that means the thermodynamic cycle may be different for these two cases. The working fluid or working system may be different. Their material of construction for the engine may be different, so that in many ways the engines may be different. But the thermodynamic cycles on which the working system operates in both the cycles have to be reversible. Then it will be reversible engines, and they will be different reversible engines. That means whatever may be the working system, whatever may be the processes in terms of the process constraint, but if the processes are all reversible, that means the thermodynamic cycle is reversible, then it is a reversible heat engine of different types, and they yields the same efficiency, they results in the same efficiency when working between the two temperature limits. So therefore, we can tell this thing now in a gist form that all reversible engines have the same efficiency, which we designate as eta R, and all irreversible engines on the other way, which varies in their working system, material of construction, processes, but irreversible. Not all the processes are reversible in the thermodynamic cycle. Thermodynamic cycle is irreversible. They vary with their efficiency. That means if all of us design some engine in practice, this will be reversible engine, practical engine. Then we will see the efficiency of all the engines developed by all of us individually will be different. One may be very smart enough to design a very efficient engine. One is not that smart enough to devise an engine which is not that efficient. That means all irreversible engine, eta 1, eta 2, eta 3, eta 4, all may be indifferent. That means eta 1 may not be equal to eta 2, may not be equal to eta 3, and so on. It's not that they are equal. That means the irreversible engine efficiency may vary even working between the same source and sink temperature, but this is same. And the highest of this efficiency of the irreversible class of engines, or the class of irreversible engines, is less than eta. That means eta is greater than eta for highest. The highest value of the efficiency what one can achieve in practice on irreversible or natural engines is less than eta R. That means the reversible engine efficiency is the highest. This puts and the performance criteria for all the irreversible engines. All the irreversible engines may vary in their efficiencies, but the highest one is the reversible engine efficiency, which is same for all reversible engines working between the same source and sink temperature. Now I will come to a very important concept or very important deduction, thermodynamic scale of absolute scale. Absolute thermodynamic scale of temperature. What is this? Absolute thermodynamic scale of temperature. This is, how do you define? It was defined by Lord Kelvin first, the absolute thermodynamic scale of temperature, then it was in use. Now this definition of absolute thermodynamic scale of temperature comes from a comes directly from the Carnot's theorem or principle, or it is a direct consequence of Carnot's theorem or principle. How? Let us see now. If there is a heat engine operating between T1, takes heat Q1 and rejects heat Q2 at a temperature T2 and develops work, we know if it is a reversible heat engine, then we know efficiency is a function of temperature. That means the Carnot's principle tells that all reversible engines have same efficiency working between these same two temperatures, thermal reservoirs, T1 and T2. T1 is greater than T2. That means analytically you can express that eta is a function of T1 and T2, because this depends only on temperature. If you change the T1, T2, then the reversible engine efficiency will change. But again, with the same sink and source and sink, same reservoirs, the efficiency of all reversible engines same. That means for a given T1 and T2 as the source and sink temperature, efficiency is a function of T1, T2, that we can write. Now efficiency can be written as W by Q1 is equal to Q1 has been done earlier, Q2 divided by Q1, that means 1 minus Q2 by Q1. So therefore one can write 1 minus Q2 by Q1 equals to function of T1. That means this is a function of T1, T2. This can be written in a different fashion, that Q1 by Q2 is some other function of T1 by T2. That means T1 and T2. That means the ratio of heat interactions by the heat engine with the source and sink is a function of two temperatures. This is some other function. That means we just write in this fashion, if 1 minus Q2 by Q1 is a function of T1 and T2, then Q1 by Q2 can be written as a function of T1 and T2. Okay. Now we consider another heat engine. Let us consider this is heat engine number 1, this is heat engine number 2, which takes heat from T2 as Q2 and rejects heat Q3 at a temperature T3 which is less than T2, which is less than T2. That means T2 is less than T1, T1 greater than T2, and T3 is less than T2, and it develops another work. Let this work is W1 and this work is W2, heat engine 2. Then for heat engine 2 we can write in the similar fashion that Q2 by Q3 is the same function of T2 by T3, because it is an unique function. Efficiency is an unique function. It depends upon the temperature levels. If you changes these arguments T1, T2, it will give the value of eta, because it is dependent on T1, T2, but the same function but with T2 and T3. And if we consider the combination of two engines together, R1 and R2 together, which develops W1 and W2 amount of work, takes heat Q1 from T1 and rejects heat Q3 to T3, then with respect to the combined system, we can write Q1 by Q3 is a function of T1, T3, is a function of T1, T3. Okay, same function. Now we can write this thing in this way, but so long we do not know this functional form, we only express in the form of an implicit function that Q1 by Q2 is some function of T1, T2, Q2 by Q3 is the same function of T2, T3, and Q1 by Q3 is the same function of T1, T3. Okay. Now if we write with certain algebraic manipulation Q2 by Q1 as Q1 by Q2, rather Q1 by Q2 as Q1 by Q3 divided by Q2 by Q3. Then we can write this Q1 by Q2 is Q1 by Q3 divided by Q2 by Q3. So therefore we can write function of T1, T2 equals to function of T1, T3 divided by the function of T2, T3 from here. That means if I just make an algebraic rearrangement, so that this gives some hints to the type of the function. not the explicit form, exact explicit form of the function in terms of the two temperatures, but at least they give some idea because of exploiting this relationship. Q1 by Q2 function of T1 T2, Q2 by Q3 is a function of T2 T3, and Q1 by Q3 is the function of T1 T3. So that we can write that function of T1 T2 is function of T1 T3 divided by the function of T2 T3. This is only possible, that means T3 should be cancelled out such a way that T3 terms from these two functions, so that it results into a function of T1 T2, and this is only possible provided the function is of this type. T1 T2 can be expressed in terms of product or quotient. However, you can tell I write this way is a function of T1 divided. Only in terms of that is a product form or a quotient type, that if function of T1 T2 is function of T1 by T2, then it can happen, because here it will be function of T1 by function of T3, here it will be function of T2 by function of. Then what is happening? That function of T1 by function of T2, if the function can be expressed this way, then only this is function of T1 divided by the function of T3. So this function can be expressed is this way, that is function of T2 divided by the function of T3. That means the way in which the heat flux is cancelled out, Q3, it becomes Q1 by Q2, the function T3 cancels out altogether, so that it remains function of T1 by function of T2, which is a function of T1 T2. That means this function of two temperatures for the efficiency will be in this form. Clear? So this now, okay, now this function of T1 and T2, phi T1 and phi T2, this is defined. Now I write Q1 by Q2. So therefore we arrive this is some function of T1 by some function of T2. Now eta is a function of T1 and T2, from which we derive that Q1 by Q2 is some function of T1 T2, and that has to be of this form from this deduction, function of T1 and T2. And this function is defined as T1. This function of T1 is temperature measured in any conventional scale existing earlier, when this absolute thermodynamic scale of temperature was not discovered or was not deduced like this. That means it is temperature on any conventional scale. This function itself is defined as the absolute thermodynamic temperature, that absolute thermodynamic scale of temperature. That means absolute thermodynamic scale of temperature. So the function itself is defined as T1, this function itself of T2 is defined as another temperature. This is conventional scale, temperature existing conventional scale. This function is defined the temperature in some other scale, which is the absolute thermodynamic scale, and this is T2. So therefore this gives the birth of absolute thermodynamic temperature scale, and this is the definition of absolute thermodynamic temperature scale, that the ratios of the temperatures equals to the ratios of the heat interactions by a reversible heat engine. That means if Q1 is the heat taken from temperature T1, now if I express this as absolute temperature T1 and this is as absolute temperature T2, then T1 by T2 is equal to Q1, the heat taken from T1 to that given to T2. So therefore this is the definition of absolute thermodynamic scale of temperature, that is the ratios of the temperature is equal to the ratio of the heat interactions by the reversible heat engines. Now the question may come, this is the concept, these are the very routine logical deduction, but concept is that, sir, then to find out the absolute thermodynamic temperature scale we have to measure the heat interactions by a reversible engine, but reversible engine doesn't occur in practice, all natural or practical engines are irreversible. Yes, this is a good question, may come, but here the answer is that this heat Q1 by Q2, that is the heat interactions by a reversible heat engine, can be expressed in terms of other measurable properties by the thermodynamic property relations from where we can measure this. So therefore it is not always that it remains as a hypothetical, since it was defined in terms of the heat transfer by reversible heat engines. Okay, so this defines the absolute scale of absolute thermodynamic scale of temperature. Okay, now we will define, we will go to the definition of or the Carnot's engine or Carnot cycle. Now Carnot was the first man, Carnot engine, who first realized how we can conceive in practice, not in practice, rather we can conceive physically a reversible engine. We can conceive physically a reversible engine that was first given by Carnot. The concept is like that. He first took a cylinder and piston. And some gas inside it at a temperature T1 and at a pressure P1 at a volume V1. And he took a body whose temperature is T1 plus dt, and heat is allowed to transfer to this through this head. Everything is insulated. And while the heat is transferred, since it is with infinite small temperature difference T1 plus dt to T1, this process is an isothermal heat transfer process, heat addition process. Slowly heat is coming, and at the same way we make this temperature T1 fixed. Since T1 plus dt, the source temperature is fixed. For this we expand or we push the piston outside, okay? And let us consider the piston has come to this state. So this state is A, and after this expansion the piston comes to this state. The piston comes to this state. This is this state B. Now while the piston expands, what happens? Even if the heat transfer is there, it cannot raise the temperature because the gas expands, and for expansion a cooling is there, so that it makes a balance to make the temperature constant. That is, isothermal process is possible with heat transfer provided it does work. So piston comes here and work is developed. Now this is the system B. Now here what we do, we make everything insulated and allow the piston to go, to a position where the gas is expanded like this. This is the another position. This we can make dotted because it is the separate figure. So from state A to state B, then state B to state C, here temperature remains same T1, pressure is little bit reduced and volume is little bit reduced. I am not showing it, but here the pressure is tremendously reduced, that in C, and also temperature is reduced because this is insulated, no heat transfer is there, and let the piston expands from this position to this position, in which we get the work, a greater amount of work we get. Now here what happens, after this is all insulated, and this expansion we make extremely slowly. Where heat transfer was made extremely slowly, piston moved extremely slowly, and little displacement is there for some amount of heat to be transferred. Then piston have a very large displacement and expansion, but very slowly. It is an extremely slow process when everything is insulated, no heat transfer is there. Then at this state, after reaching this state, we remove the insulation and make the piston comes to a contact to a, this gas, not the piston, this gas comes into contact to a cold reservoir. Let at this state temperature is T2, which is much less than T1. Now I am writing this T1, T2 in absolute thermodynamic temperature scale. So this is T2, this is T2 temperature. So therefore this will be T2 minus dt, so that this temperature is very small compared to this T2. That means the heat is transferred to this temperature, this acts as sink, where the temperature difference is infinite small. That means the heat transfer takes place at reversible condition, limiting reversible, quasi-reversible condition. And to make this T2 constant, just like the heating process, we make a displacement of this system, piston like this. That means while it rejects heat, the piston pushes the air. Rejection of heat will make the system cold, that means its temperature may decrease, but at the same time the piston pushes the air to raise the temperature, so that balance is there, because T2 minus dT2 is kept fixed. So if T2 is going lower, then the temperature differential will be higher, so that we don't want to make the temperature differential higher. That means it will be an isothermal heat rejection. Like that, it is an isothermal heat addition. T1, the system temperature was kept constant. Here T2, the system temperature is kept constant. So this is the process of heat rejection, where the piston moves here. Then at the end, last process, after this, we again, just similar to that, insulate everything, take away the sink, and make the piston from this position. It could have been better if we could have drawn below it, so that this is this position. From this position, it again comes back to its initial position. That means in this process, what happened? The gas is compressed, a substantial compression of the gas, but very slowly, just like the expansion takes place very slowly from this position, that is this position, to this position. Similarly, from this position, the gas is compressed to its initial state, so that we regain again the P1, T1 and V1. We remove this sink and make it insulated, so that no heat transfer takes place. So this way, the Carnot's thought of physically a reversible engine or reversible cycle. It consists of 4 processes. You see, this is an isothermal heat addition. This is the way we conceive it, that some air is there, it is in contact with T1 plus dt, where dt is very small, and T1 is kept constant, so by expanding the gas to a little extent, so that some heat is transferred at constant temperature T1 and always at infinite small temperature difference. Reversible isothermal heat transfer. Then after reaching this position, everything is insulated, this is removed, and this is expanded from this position to this position. Okay? Very slowly, extremely slowly, there is no heat transfer to the surrounding. So question of irreversibility cannot come. Then this comes here after the expansion. Okay? And we get work here. Here also we get some work because of the expansion. Major work comes here. And this is an reversible expansion process, and the process is adiabatic because it is insulated. Then after this, what happened? Just like heat addition, we have to reject it by Kelvin-Planck statement. One reservoir engine cannot operate. Then here, if the temperature is T2 at this position, that is T2, then this sink has to be T2 minus dt. And to make the same infinite small temperature difference dt for heat to flow to the sink, we make it a constant temperature or isothermal heat rejection by pushing the piston slowly, and it comes to this position when some heat is transferred. Then at this position, we again insulate it and very slowly compress the gas to its initial position. This way we conceive a Carnot cycle or Carnot engine. If we draw this on PV diagram, you will see that state A, let us like this, P1, V1 and T1. Okay. Now state A to B, C, okay, C to D, and final state is E, that is again A. Final state is E, or that is again A. So A to B is an isothermal process. It looks like that in a PV diagram, where the volume is increased and pressure is decreased due to this. For an ideal gas, you know, PV is equal to RT or PV is equal to MRT, V is the total volume. Then a isothermal process gives in PV diagram a rectangular hyperbola. Here P is the pressure, V is the specific volume per unit mass. So this is the this is taking place at a constant temperature T1. Then from B to C is an slow expansion process to a very low pressure and temperature, and this is very low pressure and temperature, and this is a reversible adiabatic process. So reversible isothermal process. This is reversible adiabatic expansion. Why adiabatic? Insulated, no heat transfer. Then C to D, again from C to D is a heat rejection, but at an isothermal. That means if this temperature is T2 at state C, this remains at T2. Then again, and this is isothermal heat rejection. This process is isothermal heat rejection. This is isothermal heat rejection. Okay, and then again from D to A, this is the direction of the process. D to A is again, this is the D state, this is the D state, you see D state, this is the D state to A state, again in the initial state. This is adiabatic compression. That means we see the Carnot cycle consists of two isothermal process at T1 and T2, two temperatures, T1 is higher than T2, and two adiabatic process, reversible adiabatic process, adiabatic expansion and reversible adiabatic compression. Now at this temperature heat is added, let Q1, and at this temperature heat is rejected, let Q2. And in this WBC work from B to C we get, and here we give work WB to A. WB to A. So this way a Carnot cycle is conceived, and if we write the efficiency of the Carnot cycle, as we know, is 1 minus Q2 by Q1. This is because this is the network. If WBC is higher than WBA, so WBC minus WBA, okay, divided by Q1. That means, and this equal to Q1 minus Q2, WBC minus WBA equals to Q1 minus Q2, so 1 minus Q2 by Q1, as you have already seen for a reversible heat engine. So this way if you write, and with the definition of the absolute temperature, we can write T2 by T1. So therefore, the efficiency of any reversible engine can now be expressed in terms of absolute temperatures as 1 minus T2 by T1, because Q2 by Q1 is T2 by T1, already we have proved, and this is by the definition of thermodynamic scale of temperature. We have deduced from the directly from the Carnot's principle or theorem that the absolute thermodynamic temperature scale is defined as that the ratio of the temperatures in that scale is the ratio of the heat interactions by a reversible engine with the thermal reservoirs. So Q2 by Q1 is T2, and this is not for this type of reversible engine as conceived by Carnot. For any reversible engine working between a sink temperature T2 and source temperature T1, its efficiency is given by 1 minus T2 by T1. Okay, this is the way Carnot first conceived a reversible heat engine. Okay, thank you for this module.